Hello guys. So today I'm just gonna try recording some of my math stuff. Um yeah, so right now I'm taking Calc 3 and I think the best way to learn is to document what you're learning. So that's what I'm gonna do. For yeah, just for my course, but you guys are free to watch whenever you want to. So yeah. Right now we're talking about three-dimensional coordinate spheres. I mean systems. Yeah, so we're talking about 3D coordinate systems. So this is just to help us get into the habit of thinking in 3D. Because before we used to think like there's a plane, right? And then we have a Y, we have an X. But now we're going to look at something like this. So we have an X here, we have a Y, and we have a Z. So this is more like 3D-ish, right? So that's what we're going to be doing for the most part. So yeah, initially, when we look at, let's say, this 2D, we have a point, right? And this point is what? Say this is Y, this is X. This point has a number, well, two numbers. It has what we call an ordered pair because it's a pair. It's a pair of two numbers, right? But so this is 2D. Now when we look at 3D, so 3D, so we have what? X, Y, Z. And let's say we go at some point here. Let's make it clearer. Now we have some other points, right? So let's say this is A. This is B. Well, this is B. And then this is C. So we have this ABC, which is what we call an ordered triple. Because this one's a pair. It's a pair of two numbers, right? And then this one, it's three numbers, assuming A, B, and C are numbers. So this is an ordered triple. So assuming A, B, and C are real numbers, right? So yeah, it's just like an intro. We're just looking at 3D stuff. So yeah, the first thing we're gonna be talking about, um, oops, no, it's not. Huh. Okay, screw it. Notes aren't scrolling. So the first thing we're gonna be talking about is this thing called a 3D space, right? So this 3D space, it represents points in space. So when we look at 3D space, Z, X, Y. So this is a 3D space, and similar to a 2D space, Y, X. This has ordered pairs or points, namely one could be A, B. Here it also has points, namely one could be A, B, C, or X, Y, Z. It doesn't matter, just letters. And then we have to choose a fixed point, which is an origin, right? So here, this is our origin, or the point, the ordered pair, or the point 0, 0. Here we also have our origin. This is the point 0, 0, 0, right? Does this make sense? This is 0 in terms of y, I mean, in terms of x. So this is 0 in here, and this is 0 in here. In this case, this is 0 in terms of horizontal axis, which we denote as x, vertical axis, so vertical, and then this thing that makes it 3D, which we'll just name it z by convention, because x, y, and then the last letter is z. So that's why we name it z. But you can literally call it anything. Letters are just letters, right? Okay. Yeah, so we have 3 directed lines through O, origin O. Yeah, we call it O, it's letters. Perpendicular to each other. So these are perpendicular, by the way. What we mean by perpendicular is lines that intersect and they form a 90-degree angle, or radians, pi over 2 radians. So same idea here, 90-degree here, 90-degree here, 90-degree here, even at the bottom, right? So it's all 90 degrees. So that's what it means to be perpendicular. So yeah, we're just describing what this 3D space is. So here, yeah, we have the 3 coordinate axes, and they determine 3 coordinate planes. So if we look here, let's redraw the thing. Our 3D plane, well, not 3D plane, our 3D space, right? And let's say this is X, Y, Z. So we have planes here, right? This thing all the way to here. This is what we call our XZ plane. How do we know? Well, remember from an earlier math, remember this was Y, this was X. We call this the XY plane, which is actually, funny enough, this is XY plane. This is XY plane. Right? And then the Z is just like coming forward like here. But yeah, you get the idea, I think. So that's the XY plane. They're called planes. They're called Cartesian planes. I'm not sure who Cartesian is, but they're called Cartesian planes. So this is the XZ Cartesian plane. This is the XY Cartesian plane. And we actually have another plane here, which I'll draw in green, because RGB, oh yeah, it's RBG. Anyway, so XZ plane, XY plane, and here we have the YZ plane. Yeah, a bit messy, I know. So this is the YZ plane. Right? But yeah, that's how you describe space in 3 axes, all intersected towards each other. So yeah, those are the three planes. And we can see from here, yeah, the XY plane contains the X and Y axis. YZ plane contains Y and Z axis. XZ plane contains X and Z axis, which makes sense. Now, these three coordinate planes divide space into 8 parts called octants. Yeah, it does. I mean, if you can see here, these are 8 parts. Okay, let's draw a cleaner version. So this thing here, we're gonna redraw as this X, Z, Y. So this space, you think of it like a room. This space here, oops. This is an octant. No, not an octant. This is the first space. Right? That's one space. And we actually call this I think it was the foreground. Yeah. It's because that's where everything is positive. Yeah, the foreground, right? That's where everything is positive. Because if you look at this XY plane, if we redraw that, so the XY plane, the positive values are here. Because we remember this is the first quadrant from high school geometry. And the first quadrant is this thing here. Right? That's the first quadrant. So we know that's positive. And so same idea. This is also positive because it goes up. Like this Y, this is positive, right? So kind of similar to this. This goes up. So that's positive. So this is positive. Z is positive. X is positive. Y, this part of Y is positive. So this is what we call the foreground. This like room is called the foreground where everything is positive. And we have other spaces here as well. So it's not just that. So this is the first one, the foreground. Oh, my bad. Okay, I'll just erase. Okay, the other parts are, so that was the first one. The second one is this part, right? You can kind of see what I mean. Yeah, this is the second part, right? So Z is still positive here. X is still positive, but now Y is negative. So that's another part. So we counted one, that's two. Yeah, we have other parts here. So that's one, two. Oops. And then this is the third one, right? That's the third one. So Z is positive, X is negative, Y is negative. So yeah. And then the fourth one is this one, right? That's the fourth one. And now you might be wondering, where's the other four? Well, it's down here. This is the other four, right? Oh shoot, messed up. This is the other one. There's like a roof here. That's one, and then this is two, this is three, this is four. So all in all, 4 plus 4 is 8. So that's where those octants are from. But yeah, those are the octants, right? And then, So we covered that. Yeah, first octant is positive because the x part, the y part, and the z part here, they're all positive. And then, yeah, here now I kind of said this earlier, but we're going to reiterate. So this is telling us that we can plot, just like in a 2D Cartesian plane, we can also plot ordered triples or points in space. So not in a plane, in space, because it's 3D. And yeah, we're just putting random numbers here. So, okay, I'm going to show this. So let's redo our space thingy again, or what we call a 3D coordinate system. So this is my x, my y, my z. All right, and let's say we want to plot a point here, and we'll call it like point. Now, how do we go about this point? Well, we can be like, okay, let's go x this amount of times. Let's say that's what? That's a. It could be 1, could be 2, but we'll just do letters for now because we want to make it general. And then now we can go a certain y times. So we can go like what? Y b times, right? This is a different color. That's boring. Right? And then now we go z times up or down. And we call that c. So a, b, c. Yeah, like the alphabet. And so this point is a, b, c. Right? We can do that. Or we can say, oh, I want this point. We can go like what? We can go d times here. Yeah. No, I'm kidding. That's wrong. We can do d times here because you have to go to the x thingy, right? You have to go to x first, and then what did I put? Red because we red, and then we do y does negative, obviously. This is d. This is what's after d? E. And then we can go up here, f. Oh, handwriting. F. F. So this is what? The point D, E, F. You can just name it like point, other point, right? So this is the point D, E, F in space, right? So yeah, we can plot more points. So we can just, yeah, it's like a Cartesian thing. We can plot it anywhere. So yeah, that's the idea there. And then, oh, my thing lagged. Yeah, so like this. So we go A certain number of times, B certain number of times, C certain number of times. They're real numbers, so it just means they're numbers, basically. And yeah, we can see this idea that it kind of um, makes like a box in a way. Because here, when you load this, we go like A times, and then we go like B times, we go C times. And we kind of have this, like, we can trace in the certain octant, we can trace like, oh, looks like a box. And we can actually get points here, right? So we can see like, oh, this is uh this is the point we initially got, the ABC, right? And then this is 0, 0, 0, which is our origin. And then this is A 0, 0, because we go A number of times. So it's just like a regular 2D, but it's just 3D version. So we go in our X, we go A number of times, 0, Y, 0, Z, And then here is, we go A number of times, B number of times. We don't go Z number of times. And then, yeah, it's pretty much the same. Now we just keep doing that, trace everything, and we get like a box of some sort. So, yeah, pretty cool stuff. Now, yeah, it still has these terms. And we have this thing called a Cartesian product, where basically if you just multiply, well, the plane, the space, you get a set of all ordered triples of real numbers. And yeah, it makes sense. Like, there's so many possible points you can get in this space. You can get like this point, this point, this point, this point, this point. And that formula there, the real numbers, so this R times R times R, which is just R cubed, is basically the set of all X, Y, Z numbers you can get, right? And the entire thing. Yeah. So there's a notation in math, but I mean, yeah. And then that's when X, Y, Z, they're all basically real numbers. Yeah. So that's the idea of that. It's just a notation. Yeah. So here, yeah, A is X coordinate, B is Y, C is Z, C is Z. Yeah, and then we call this a 3D rectangular coordinate system. Very complicated. Like, the wording's so complicated, but it's really simple. Like, you can see it's a shape. Anyway, yeah, and then now we move on to surfaces and solids. But yeah, that's the idea of it. Okay, how do I format? Okay, yeah, we did 3D space. Okay, yeah, so we're moving on to surfaces and solids. So for surfaces and solids, yeah, in 2D geometry, Cartesian product is r to the power of 2, r squared, which is, again, if we do the math thingy, that's just, okay, let's write it. So in 2D, the product, or the Cartesian product, is basically this r, which is just a real number, times another real number, which can be r squared, which is, again, just the set of an ordered pair, such that these, or each of these, we call them real numbers. Each of these letters are real numbers. So these are the set of points that we can get in a Cartesian plane. Yeah, we call this a Cartesian plane in 2D geometry. Yeah, it's just a set of points you can get. All right. And then in 3D, I mean, I already said it. So in 3D, it's the set of all points, and I mean all ordered triples, all points you can get in space. Right? So that's that. Now we move on to example 1. And the question here is, what surface in R cube, or in the set of all the possible points, is represented, all possible points in space, is represented by the following equations? So in example 1, we have this idea. I'm kidding, we don't have an idea. Z equals 3. So that's the first example. Right? So what surface can we represent when Z is 3? So we remember, yeah, let's put that. So A is Z equals 3. Let's draw our, oh shoot. Let's draw our XYZ space. Before I used to call it XY plane. Now it's XYZ. So XYZ. And then Z is 3. So that's non-negotiable. Z is 3. So Z is 3. Let's put here. Z is 3. Now, we have to describe the surfaces we can get if Z is 3, right? So we can look back at our original, our conceptual idea that our cube is the set of all the possible points in this 3D space. But now we want Z to be 3. So what does that mean? This means that we want all the possible points, but Z should be 3. So it means we could have any point. So we could have any point, and I mean any point in space, as long as Z equals 3. That's non-negotiable. Z is 3. So the way we can write this is the set of these pairs, these triples, these ordered triples, as long as Z is 3. No more, no less, Z is 3. So how do we, this is a mathematical way of doing it, but what's the visual? Because everybody likes visuals, right? I like visuals. Visually, X, Y, Z. Z is 3, and it can only be 3. So I guess we could, I don't know, this could be a surface, right? Because Z is 3. So this works. We describe the surface, Z is 3. That was a question. I think that's it. Yeah, what surface in R cube is represented? And yeah. Yeah, Z is 3. And in terms of points, if you want to apply this thing, what we just described, it could be any of these points. Yeah, the plane just goes infinitely. Yeah, we could cover that. Like that. Bigger plane. But as long as Z is 3, then we should be good. So these are all the set of all possible points as long as Z is 3. Let's erase that. Looks ugly. Looks like blood. What the frick? Anyway, so yeah, that's the idea. Okay. And yeah, it's also parallel to the XY plane. It is parallel. What parallel means is that you have two lines, or let's say in 2D geometry, you have two lines. Oh, it looks like they'll intersect, but they shouldn't intersect. That's what parallel means. Parallel lines. Yeah. So if you have a crush on someone and that crush doesn't like you back, then you guys are parallel. Anyway, okay. So those are parallel lines. But we have 3D. So in 2D, it's parallel lines. In 3D, we'll go back to the example where Z is 3. We have parallel planes. Magic, I know. Crazy. We have parallel planes. So this is an XY plane, right? Wait, forgot to label. X, Y, Z. This is the XY plane. And this is the surface that we just got like 5 seconds ago. And we can see these two planes, they never touch each other. So if they never touch each other, then that means they're parallel. So we call these parallel planes. These two, because they never touch. Amazing. Okay, what's next? Okay, another exercise, y equals 5. So that same idea that we did here. Yeah, this was example A. Yeah, so this is now B. Y equals 5. Now, the mathematical definition is the set. This is the set of all ordered triples, all points, as long as y is 5. Right? So same idea. So we could have any point in space as long as we just change this to y equals 5, as long as y is 5. So what's a good representation of the surface? So a good representation of the surface, well, it's when y is 5. Right? Same idea. And this, I'm just shading it. And then this notation, if you want to apply it, it's just a set of all possible points in the plane. Again, it looks like blood, but yeah. Next time I should do like what? Green? And then this should be naturey looking. I'm kidding. Okay. So this is, yeah. This is a good representation of the surface when y is 5. And we have a note. So given an equation, does it represent a curve in r squared or a surface in r cubed? So for example, x equals 2 represents a plane in r cubed, right? So we can see here, what we're basically looking at is we're trying to consider this thing called context. Because when we say x equals 2, in r squared, x equals 2 is a vertical line. So we want to consider context. Yeah, let's add the note here. Because this is confusing if we don't give enough context, right? So we want to consider context when we're making these equations. X equals 2, y equals 5, z. No, I'm kidding, not z. In a 2D perspective, x equals 2, well, you already know what x equals 2 is. It's this vertical line where this is 2, where this point is 2. This is the origin, right? Makes sense? Oh yeah, let's say this is y, this is x. Y equals 5. Yes. Y equals, oh shoot. Y equals 5. I'll not take out the origin. Y equals 5 is this one. This line is y equals 5. This is in 2D, right? How about 3D? Well, it's different. Previously, those were lines in a plane. Here, these are planes in space. So that's the difference. So this is x, y, z. When x is 2, remember, this is our foreground, right? Foreground. Ooh. In our foreground, this is when x is positive. So here, probably here. This is origin, assuming it's origin. This is 2. So x equals 2 is this. I can't draw. Like that, right? So these are what? The set of all points as long as x is 2. Right? And then y equals 5. Make it green. Y equals 5 is, I don't know, probably somewhere here. Oh, I covered it. So this is the set of all the ordered triples as long as y equals 5. So this is a plane. These are planes in space. But in 2D perspective, these are lines in space. No, lines and planes. Lines and planes. But in 3D, these are planes in space or on space. My English is not Englishing. But oh shoot, I deleted. So yeah, that's the idea, right? So it's important to consider context. Are we doing it in r squared? Are we looking at it in r cubed? Those types of things. Oh shoot, wow, we did the exact same thing. Or we didn't. Yeah, so if you look at this example, this is from a textbook. X equals 2 represents a plane in r cubed, but x equals 2 can also be a line in r squared in 2D analytic geometry, or just in 2D. So in general, yeah, this is, okay, so this is where it gets algebraic. K is a constant. K could be 2, K could be 3, K is any real number, I'm assuming. If x is K, then this is a plane parallel to the YZ plane. How do we know? We can test it, obviously. So what it's saying here, okay, we redraw our, how many times have I drawn this? We redraw our thing. Let's say x is some k. Some k. Could be 0, could be x, could be y, could be k, doesn't matter. This is a plane of x equals k. This is parallel, meaning it never touches the yz plane. What's the yz plane? Well, the one behind. That's the yz plane. And these two never touch. Right? So these are parallel planes. And same idea for these other what assumptions? Yeah, y equals k is parallel to the xz plane. Z equals k is a plane parallel to the xy plane. So those are some general ideas. Yeah, and then in other words, if x is 0, y x equals 0 is the yz plane. Y equals 0 is the xz plane. Z equals 0 is the xy plane. Okay, let's try one of these. Let's do one here. We'll do the z equals 0. So if we draw our thing, x, y, z, z equals 0, where z equals 0? Well, we look at z, it's this origin, z equals 0, right? What is the xy plane? The xy plane is this one. What's z equals 0? What's the surface that z equals 0 represents? Well, it's also this one. Remember from that previous example? What's the surface that z equals 0 represents? So z equals 0 is the set of all possible points that is as long as z equals 0. So it's the set of all possible points as long as z equals 0. And it is the xy plane, funny enough. So this is the xy plane. And yeah, it's the same for the first two. Okay, now we move on to example 2. Move on to example 2. So example 2, we're asking which points, which ordered triples x, y, z satisfy these two equations. So we'll just write that down. So in example 2, we're asking which points satisfy those two. What was it? X squared plus y squared. This one, I think. Yeah. And then z is 3. Which points x, y, z. Right? Now, how do we do that? Well, here's an explanation. Since z is 3, actually, let's draw it out. Usually when we see something like this, we draw it out. Draw it out. Right? So we do our typical, yeah, we keep doing this. X, Y, Z. Z is 3. Where is Z 3? Where is Z equals 3? Here, right? And what's the surface that represents? Well, it's this one, right? Now, what is x squared plus y squared equals 1? If we remember from 2D, this is basically the unit circle. Given some plane, or let's say this is the xy plane, this circle is denoted by this equation. It's the unit circle, right? Okay, but this is from a previous course, pre-calculus course. So yeah, this is a unit circle where this radius is basically 1. So this is 1. So how do we apply that? We remember right now what we're learning is that this plane is the set of all possible points as long as z is 3. So the question again was which points satisfy x squared plus y squared equals 1 and z equals 3. We already got the z equals 3. Now how do we apply this x squared plus y squared equals 1? Well, this one. This x squared plus y squared equals 1 is in this plane, right? Before, how we used to do it was everything, we just plotted it out in this xy plane. So it would be initially here, right? This is the same thing as this one. But now, we're looking at a different plane. It's not the xy plane. It's a plane parallel to xy plane, but it's not the xy plane. So it's this plane here. And we're plotting the points that satisfy x squared plus y squared equals 1. So the question is, which points satisfy both of these? Well, these points here. And these are an infinite number of points that we can't count. Or at least I can't, because I'm lazy. But yeah. These are an infinite number of points in the xy plane. These are infinite number of points in the plane where z is equal to 3, or in the surface that best represents z equals 3. Amazing. Okay. So that's that. And that's the exact thing I did. Yeah. And the radius is still 1. Okay. Now we move on to another example. Here, we're using that same unit circle equation. What does the equation was the unit circle equation represent as a surface in R cubed? So what does this represent as a surface in R cubed? Well, given this thing, or this equation, it has no restriction to z, right? So any point in this that satisfies the unit circle equation could lie on any circle in any horizontal plane because there's no restriction for z. No, don't know why I did that. So that means all possible horizontal circles, yeah, we call them horizontal because it looks horizontal from here, kind of. All horizontal circles that satisfy the unit circle equation, and z is no restrictions for z. So yeah, it basically kind of looks like a circular cylinder with the radius 1. That's the idea, right? Z could be anything. I mean, if we plot the thing again, Z could be anything. Z could be 0. Z could be -1. Z could be -1 million. We have this Z plane here. We have a Z plane here. Oh, and we have a unit circle here. You could have a unit circle here. But if you think about it, it's basically an infinite cylinder, kind of. It's kind of like an infinite cylinder, right? And this could go on and on and on. Because Z could be any plane. Could go on. Okay, this should be the exact, because they have the same radius. My drawing's just bad. But it's like an infinite circular cylinder, right? So yeah, that's the idea. Okay, next. What solid region in R cube is represented by x squared plus y squared less than or equal to 1? And z is in between 2 and 4 inclusive. So it includes 2 and 4. Well, it's a portion of a solid circular cylinder with the radius r less than or equal to 1. How do we know that? Well, okay, let's solve this. What region does it represent? So we keep doing like, what region does it represent? What surface does it represent? So when you look at this unit circle, and when we say it's less than or equal to 1, well, the standard equation of a circle is x minus some center. Okay, let's call this, do this. C1 is basically the x coordinate of center of circle, or honestly any shape with a curve. But yeah, and C2 is the y coordinate of the center, right? Yeah, this is just from a little pre-calc course. So from 2D, we have this circle. C1 and C2, this is the center, right? C1 and C2 are here. So actually, the equation is sum x minus C1 squared, sum y minus C2 squared is the radius times itself. But we can see here that this C1 and C2, if it's a unit circle, it's basically just 0, right? So we say this is 0, this is 0, and we remember that the radius is 1. So my r squared is 1. So that means we have x squared, simplifying, y squared is 1, which is that same thing we have here. Well, no, not here, here. So these are the points exactly in here, the points exactly there. But now it's asking the points less than or equal to 1. So if we're saying less than or equal to 1, then let's say this is a circle, right? Let's not impose coordinates. This is a circle. If it's equal, it's everything in this blue line, in this blue curve. If it's less than, it's everything inside. And I mean everything. So it's everything inside. If it's less than, right? Now when we say if it's the points greater than 1, and if we draw this out again, it's everything outside, infinitely outside. All the points outside. If it's greater than or equal to, it's all the points within the circle and outside the circle. Right? So that's the idea. Now, where was I? I digressed. So yeah, x squared plus y squared is less than, oh, it's lagging. X squared plus y squared less than or equal to 1 is everything within and inside the unit circle in this case. And z is somewhere between including 2 to 4. So let's, oops, next last one. Let's describe that. Oh, let's add it. Let's add this other thing here. So 2 is between 2 and 4, including 2 and 4. So if we do our XYZ thing again, our space, what is Z? Z could be 2. Z could be 4. So it could be this plane, or it could be this plane. I can't draw it, but you get the idea. It's all the possible points as long as Z is 4, or it's all the possible points as long as Z is 2, or Z could be 3. It could be, it's all the possible points in between. There's like, because if you look at it, it's like a box. It's all the toys in here, right? But that's if we don't look at that. It's all the possible points in that like box thingy, if you look at that. Because it's in between the z equals 2 plane and the z equals 4 plane, right? So it's kind of like a box full of toys with like a size of 2, because 4 minus 2 is 2. Or yeah, points. So that's the idea. Now we want to take into account this thing here. So we remember from the previous example where we did it once, right? Now let's do it again. So if z is 2, then our unit circle is probably what? Probably like that, maybe? If our z is 4, probably like that. And now it's like a cylinder. Because we include even z equals 3, z equals 3.5, I don't know. We include all that. So now it's not a box, it's a cylinder. But then we also include, so we're asking where are the points. So we include these points within, but it's also inside. So we also include the points in here. And it's the same for all of them. So it's like a, well, it's points everywhere, right? That's the idea. So it's like a circular cylinder, but we include all the points inside z equals 2, in between 2 and 4 of the z-axis, right? So that's the idea. Okay, now I messed up my drawing because I put so many points. But yeah, to summarize, it's just 2, 4. Simple and easy. That's how you describe the surface. There. When z equals 4 and z equals 2. So if you read this thing, it's a portion of a solid circular cylinder with radius less than or equal to 1. Because we said, right, if it's inside the circle, initially radius is 1, it could be 0 0.7, 0 0.5, 0 0.1, 0. So it's everything inside that circle. That's why it's a radius less than or equal to 1. And it's centered at the z-axis. And it's between planes z equals 2 and z equals 4. Right? So that's the first thing. We did like what? X squared plus y squared equals 1, and z equals 3 here. Right? And then I did this. So the points are everything in this line. That's it. Right? And then here we did a cylinder x squared plus y squared equals 1. We didn't specify a z. We did that before. This is when z is k. Right? So these could be any horizontal cylinder as long as it's in the z-axis, obviously. It's centered at the z-axis, but there's no limit to what z restricts it to be. And now here, oh yeah, and then the points are just within. I don't know if it's on. It's on here. And there could be like another circle here. And the points are here. Right? It's just there. It doesn't go inside. Radius is still 1. And now if you look at this last example, the solid region where x squared plus y squared less than or equal to 1, and 2 is less than or equal to z, so z is in between 2 and 4, which we just did earlier. It's this thing, right? And the points are not just on, but also inside. There are also points inside. So it's everything there, right? So yeah, that's the idea. And then now we look at example 3. So example 3 is just saying to describe and sketch the surface in R cube represented by y equals x. So what do we know from a previous course? Let's actually do that real quick. From a previous course, y equals x. Let's just write the example. So example 3 is what's the surface it represents in R cube when y equals x. So what does y equals x represent in R cube? So if we look at the 2D perspective, y equals x is basically this thing. That's it. Because whatever x is, that's what y is. So if x is 0, say this is x, this is y. X is 0, y is 0. X is 500. Oh, that should be a line. My drawing is bad. Y is 500. Algebra. X equals y. When x is 500, y is 500. Right? But now we want to make it 3D. So well, first of all, we sketch. So we do our z, we do our x, we do our y, right? Now what is y equals x here? Now if you look at this, it doesn't say what z is. So we can note here, z has no restrictions. Unlike the previous one, we said that z was in between 2 and 4, but here z could be anything. Could be a million, z is a million. So that's like somewhere far, somewhere far, and then a plane there that's located centered at z-axis, but z is a million. Could be z equals 0, could be the origin. Could be z is 5, it'll be somewhere here. But again, there's no restrictions. So what's that? It's the set where it could be any point, right? But here, if you look at this, x, y, z are real numbers. That makes sense, but we already know that. But since x equals y, we can just change y, right? Let's rewrite the original. X, y, z is a real number. It's a real number. It could be 1, 2, 3, negative 5, whatever. But we can change this. We can just say that's quite easy. We just change this to be x. So it's the set of all possible points where x, z is a real number, right? Now, how does that look like? That's mathematical, but how does it look like visually? Because I like visuals. Well, we can start when z is 0, because that's the easiest, right? We already have that. So when z is 0, let's draw this properly. When z is 0, so when z is 0, it's the xy plane, right? Then it's just this thing here. That's y equals x. When z is 5, then it's like that. When z is negative, say negative what? Negative 7. I don't know, I'm thinking of these random numbers. Then it's here. And if you kind of like reverse it a bit, if you look the other way around, it should look something like this. How do I do that? You have an x, you have a y, z. I made it look like x, y. That blue thing, it's kind of like that. So it's kind of like this. And it's lower. Could go on and on and on. Right? So if you look at the example, because I'm ugly at drawing, it's kind of like this. But this is just a part. It's a part of y equals x. Because you're missing this part. Could go on and on and on. It's infinite. Because there's no z restriction. Again, there's no z restriction. That's why it's infinite. Okay, no, it is not racing. That's funny. So that's what, again, yeah, that's what the surface y equals x represents in our cube, right? Yeah, and then there's just the mathematical notation. Kind of wrote it wrong, but yeah. It could be any point x, because y equals x. This is y, x, z, any point, and x is any real number, and z is any real number, or any number, except complex numbers, like imaginary values, nothing of the sort. And then, yeah, this is a vertical plane that intersects xy plane. It does intersect, right? This is the xy plane. This intersects this plane, intersects here. Actually, I don't even know why intersects here. This whole thing. Kind of like that. It just goes on and on and on. Intersects there and goes down. Okay? So that's the idea. So that's fun. Anyway, yeah, and then k is some constant because we didn't specify what k is or what z is. Z could be anything, no restrictions. Okay, now we move on to distance and spheres. So those were surfaces and solids. Now we move on to distances and spheres. So what is that? I don't know. We'll find out. Distances and spheres. Well, let's look at it. So we actually have a formula, a distance formula that we discussed in pre-calculus or even algebra, right? Where you're given 2 points and you want to find the distance between those 2 points, right? So let's say in algebra, or even like anything, you're given a car. What's the distance to this person? Let's say this person is 5 meters away. This is 0. So obviously, their distance is 5 meters. You could take out the meters. Their distance is 5. We could then change these to points. This point, this point. 0 to 5. We could then use a coordinate system, a 2D. Or we actually, let's make it more simple. We could do a number line. You know what a number line is, right? This is 0. This is 5. And then now we could do a coordinate plane. No, not, why am I saying coordinate plane? Yeah, it's a plane, yeah. Now we have the x and the y. This could be our 0. This could be our 5. Right? But now what if, let's say, I want to go from 0. Oh, shoot. I'm not erasing. I want to go from 0 to what? To here. I don't know what that point is. This is what? 0, 0. Okay, let's say this is 5. Let's give points. This is 3. So this is 5/3 or 5/3, the ordered pair. But what's the distance? Visually, this is the distance. But what is that? Well, we could do something like we did in, I think it was algebra. We call that the Pythagorean theorem. And we can make this kind of like a shape. You can copy it. This is 0. This is 5. This is 3. Right? This is 3, 3, 5. And now we just change that thing. Uh-oh. Ah, why is it doing that? No. Whatever. Okay. Now we can change this 5 and 3. And what do we know about Pythagorean theorem? Well, we have a formula for this. Let's say this was A, this was B, this is some value C. Probably you learned this, but A squared plus B squared is C squared. So C is square root of A squared plus B squared. right? So if we apply this thing, now we're trying to find C. Our A is 5. So 5 squared plus 3 squared, 25 plus 9. I'm going to admit I'm not good at math, arithmetic, so I'm going to calculate that. And that's square root of 34. So that means this is square root of 34. That's a number, right? So this is square root of 34. But we actually have another formula for computing the distance here. And we call that the distance formula. I know, very, very original. The distance formula. And what this is saying, or what this formula is saying, or what it makes uses of, it makes use of coordinates, right? Because let's say this is 0, 0, right? And then this is 5, 3, and then this is 0, 5. Now, if you're given coordinates, we can use the 2D distance formula, right? So we just say, yeah, this is some xy, some xy. The formula is the distance, which is some x from a different point minus an x from the other point squared. And then I add that to y squared, y1. Now we can look at this example here. 0, 0, yeah, let's do that. 0, 0 is my x1, y1. Could be my x2, y2, but I mean, this works. And my, what was the other one? 5/3, my 5/3 is x2, y2. Now we just apply this distance formula and watch the magic. It's not magic, it's someone already did this. Now we just plug in the values. X2 is what? 5. X1 is 0. Y2 is 3. Y1 is 0. Boy, would you look at that. 5 squared plus 3 squared. Same idea here. And we get the same answer, obviously, because why bother solving it when you already see it, right? So that's the idea of that distance formula. But actually, now here's the new topic. That's for 2D. 2D. What if we have something for 3D? Well, funny enough, we do. Let's try. We have this thing, right? Z, X, Y. And we want to find the distance from the origin to, I don't know, some point here. So we go this number of times, this number of times. I can estimate. This number of times, this number of times, this number of times. So the distance from this point to the origin is that, right? Graphically. But how do we make a formula to find this point? Well, we actually already have a formula. We just add the z, basically. So if our 2D was this x2 minus x1 plus our y2 minus y1, then for our 3D, we're just adding a z. That's it. So when we add a z, it's this x1, y, y1, z2, z1. That's the only difference. That's the formula. Now, how do we apply it? Well, I don't know. Let's try doing the thing again. Let's try putting real examples. So this was 0, 0, 0. This is say 5 to 5 to 6, maybe? What's the distance between those two? Well, we could say 0, 0, 0 is x1, y1, z1. 5, 3, let's say 2. 5 to 5 to 6 is x2, y2, z2. And now we just plug it in the formula. So we have 0, no, not 0, x2, so 5 minus 0 squared, 2 minus 0 squared, 6 minus 0 squared. I don't know what this is. 25 plus 4 is 36. And 29 plus 36, then I square that thing. Yeah, so square root of 65 is what I got. I don't know. You guys can check, but this is the distance. 65. So this line here has a length of square root of 65. So that's that. Okay, and then yeah, we actually have a proof here, proof based. We're using we're proving it pretty much. But we're not gonna get into that. Because it's advanced. But anyway, yeah, and then we have this exercise, find distance. Then we just plug it in the formula, then we'll. Okay, now we're gonna do something different, a little bit related, but this time we're not gonna do a box. We're gonna do a 3D circle, a sphere. Okay, let's try this. So a sphere with radius r and center C, HKL, is defined as set of all points P, X, Y, Z. Oh no, what is it? Whose distance from the center is the radius. So we actually have a pretty good visualization here. P is only on, I'll not click my mouse. P is only on sphere if the distance of BC is exactly R, right? So we can actually derive a formula for this thing. Now we're talking sphere distance. And it's kind of similar to our 3D distance formula. X, Y, Z. We have this sphere. Okay, my sphere is ugly. We have our center. Just say that center. That center, let's do letters, has real numbers HKL. It could be anything. And we have a radius. Amazing radius. And we have some point here that is ABC. Did we do ABC here? Or did we do X? I think the best way is to do X. Yeah, let's do X. But it could be anything. It's just easier. And in my eyes. I'm kidding. Yeah, and then this is a sphere. I can't draw a sphere, but this is a sphere. Okay, now what's the distance between B and C? Well, it's R, right? The distance between P and C. This is how we write distance. It's like this thing is basically R, the distance of R. Now, what's the formula? Well, we use our distance formula, right? So our distance formula tells us that we just subtract each of them and we square it. So this x minus h squared, y minus k squared, z minus l squared. That's the formula. So just to write it out, y k squared, and then z minus l. That's l. It's not 1. And we can just plug in any value and we'll be able to solve a distance using sphere. But at the end of the day, it's still the 3D distance formula. Yeah, x minus h. We could do any letters, doesn't matter. And yeah, boom shakalaka. We've now defined the equation of the sphere. Because remember, this thing, just rewrite it. Z minus L. We can square both terms, and now we get something like R squared, and this cancels out the square root here. And this is basically our standard equation for circle. No, not, I'm kidding, not circle, sphere. Right? And now we can use this to find points that we want. So we can find 3, -1, 6. If this is the center and it's passing through 5, 2, 3. And well, I'm not going to go through this anymore, but you just plug it in the formula. You get a certain distance, which is 22. And this is applicable to any numbers. Okay, now we try something a bit different. Let's do one last one. Yeah, let's do this one. So example 6, we show that x squared plus y squared plus z squared plus 4x, that entire polynomial, is equal to 0, is the equation of the sphere, and then we find the center and radius, right? Okay, let's try this one. So this is a hard algebra example. So we want to show that, I forgot what it was, what the equation was. Okay, what I'm gonna do, since I'm a lazy guy, is I'm gonna copy this thing. I'm gonna paste it here. Okay, let's do that. Boom. Technology is amazing. Okay, we have this. Now, how do we set this up? Here's our task. Show this is equation of sphere. So we want to show that it's the thing we got earlier. We want to show that it's this. Or the other one. Could be this. Any of them work. Right? Now that's one thing that we have to do. The other thing is, if we now proved that this is an equation of a sphere, now we want to find the center of the sphere and the radius of the sphere. So how do we find that center? Well, our center is just this one, that consists of these 3 points, an ordered triple, right? And now how do we find the radius? Well, r. We just have to find that. Okay, so let's do this step by step, yeah? So what we're gonna do is we're gonna put all, I'm gonna say letters. Put all letters on one side numbers on the other side. So it's really just algebra manipulation from high school. So let's do that. So I'm going to do this a bit quickly. So x squared plus 4x plus y squared minus 6y plus z squared plus 2z equals -6. So we put everything with the letters in one side, numbers on the other side. Did I miss anything? Let me check. X squared, y squared, 4x. Y squared, 6y, z squared, 2z, 6. Okay, we got everything. And now the next step. So how do we get this to kind of look like this? That's our goal, right? Well, we want to do this thing called complete the square, which is an algebra technique. So to complete the square, we actually have a formula for this, which is ax squared plus bx plus c, ax, I think it was plus b 2a squared minus b2 squared, and then plus c. I think it was that, right? Yeah, it was that. So we just want to apply that formula to here. So here my a is a 1, my b is 4, my c is 0. So it's nothing. Now, how do we do this? Well, we can just plug in the stuff. So this is x plus 4 over 2 minus 4 over 2 plus 0. Do we need to add that? I mean, no need to. Then we have x plus 2 squared minus 4. And then we do the same thing for these. So we did this part. Now we're going to do this and then this. So we're going to do y squared 6y. Then we get y minus 6 over 2, y minus 3 squared minus 6, minus 9. And then our z squared plus 2z. So z plus 1 squared minus b 2 1 1 minus 1. All right, checking my cheat sheet. Yeah, I'm right. Okay, and then we just want to put them all together. So it's going to be x plus 2 squared minus 4 plus y minus 3 squared minus 9 plus z plus 1 squared minus 1. And that's going to be -6. Yeah, so it's this thing, this thing, this thing, this thing, this thing, this thing. Okay, now we're pretty close. We just want to isolate every letter again in one side and then every number in the other side. So I'm going to do that quickly. X plus 2 squared, y minus 3 squared, z plus 1 squared equals -6 plus 4 plus 9 plus 1. What is that? Let me calculate that real quick. So that's going to be 8. Amazing. Now we have it in the form we want it to be. I think. Let me check. Did I get it? Yeah, I got it. Okay. So now we have it in that form. So we proved it. This is one of our answers. We showed that this is indeed equation of the sphere. Now, how do we find the radius and the center? Well, for a radius, you just look at this thing, right? From earlier, yeah, r squared. Now we want to find the r. So we're saying r squared is 8. So r is square root of 8. That's it. Or you could, if you have OCD, I'm kidding. If you want to make it cleaner, it's 2 square root 2. And then the center, well, it's these things. But no, this is a plus, right? So if it's a plus, so just a tip, this is the same as x minus negative 2. And we want it to be in that format because here it's looking for negative, right? So our radius is going to be negative 2, 3, negative 1. So that's our center and radius. And now we can do some amazing stuff with that. Yeah, same idea. Oh, I just realized I had a plus here. Wait, I messed up. Hoo-hoo. Yeah, I think I messed up somewhere. Uh-oh. Oopsies. My bad. Sorry. Where I mess up? 2 minus... Oh, this was a minus. How come I had a plus here? Oh. Huh. So my notes are wrong. Or did I mess up something? No. No, my notes are wrong. Yeah, because if you look here, it's z squared plus 2z. So this should be plus. So yeah, I'm wrong. Yeah, my notes were wrong. Yeah. So this should be a plus, 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 and then plus, plus. Yeah, and then this should be negative. Anyway. Okay, last example. Where did I go? I went from all the way to. What region in R cube is represented by the following inequalities? So we keep doing this thing where we're asking what region is represented. In what context? R cube or R squared? So in R cube, what is this thing represented? So, okay, we have this 1 x squared y squared z squared. I think it was 4, right? Yeah, it should be 4. Yeah, and then z is less than or equal to 0. Okay, now how do we go about this thing? Well, we can first put a square root. So this thing. And if we put a square root there, it says that points x, y, z has distance from origin at least 1 and most 2. Now, how do we know that? Well, from our distance formula, which was here, x squared plus y squared plus z squared. That's how we know about that. So we can actually simplify this thing to be the square root x squared, y squared, z squared less than or equal to 2. Because we're taking the square root of each. Square root of 1, square root of 4, So that's where we got that thing. And this is the distance, right? So actually, funny enough, we can derive this even more. X minus 0, y minus 0, z minus 0. Now we have a center. Our center is 0, 0, 0. And the distance of here, so distance from 0, 0, 0 to xyz is the other xyz. Let's make it in green. Okay, that's ugly. To xyz is in between 1 and 2 in English. Inclusive. Let's make it inclusive. So it could just be 1 and 2. Right? That's what that's saying. Now, how do we visualize that? Well, we actually kind of already have it here. Now, how do we, was that the only one? I think there was another one. Oh, z is less than or equal to 0. Okay, so that's the other condition. Z is less than or equal to 0. So if we were to draw that thing here, so we look at z again. X, Y, Z. If z is less than or equal to 0, we're only looking at points here and under z. We're looking at planes below 0 and exactly at 0 in terms of z. So that's the first thing. But now we have to consider the fact that we have another condition, which is this one. I don't know why I look like I crossed it out. That condition. So let's say, hypothetically, let's make our plane here. And we want to look at this part, right? So what do you think is going to happen? Well, I mean, if we look at it from here, z is less than or equal to 0. This is a sphere. Why is it a sphere? Well, from our previous example, see how this equation is a sphere? It's the same idea. This is a sphere. This thing's a sphere. Right? I could have the equation of x squared, y squared, z squared equals 2. And this would give me a sphere with the radius square root of 2. Or I could have 4. This would give me a sphere with radius 2. Right? So that's the idea. So yeah, based on the thing there. Or actually, we can do it in one of these. Why not? Let's do one layer of the sphere. Let's say z is here, right? Z could be like what? Like 4, -4. Actually, wait, the simplest case is when z is equal to 0. Let's do that first. When z is 0, we have this thing. Now my z is 0. And this is in between 2 and 1. What is this? X squared plus y squared. Right? Because it's just a 0. And now if you look here, when z is 0, it's just an xy plane. We're just looking at it from 2D. We're looking at it from 2D. This square root of x squared plus y squared. And let me check the... Yeah, it's just 2. We have this thing. We have either x squared plus y squared is equal to 1. And then we have this thing where x squared plus y squared is equal to 2. Actually, let's focus on the upper bound. This is actually the same as x squared plus y squared equals 4. Which is just a circle equation. It's this one with the radius 2, right? This thing is this one with the radius 2. And if we look at something like 1, it's the same idea. And if we apply that to our 2D, it's probably somewhere here with a radius 2. So this must mean this is negative 2, right? Yeah. And then now we keep going down. It's just a sphere. Because that whole thing is just a sphere. Initially, it was supposed to be a full sphere, but there's a restriction that z is less than or equal to 0. So we're only looking at a half sphere, right? So that's that. Yeah, it's fascinating. You can just like make complicated shapes with these formulas. But yeah, something interesting. Anyways, that's it for 3D stuff. Yeah, anyway, I'm just doing this because I want to document my learning. I'm trying to see if this approach is helpful. So I'm gonna keep doing it because so far it's helping me. Because it's also my first time learning this course, so we're gonna see. But yeah, I'll see you guys in the next video if I were to make one. Yep. See you guys.